Okay. So thank you. So good morning, everyone. And yeah, I'm gonna. It's difficult to follow you actually. Well, I will take as a starting point actually your last statement, and say the science is clearer than ever. So I'm a climatologist. So what do we have to do now then if the science is so clear? I don't think it's that the science is so clear in many points. So that will be my point of view in this talk. So I would like to give you a first, the ideas that we have. Yes, no, it's not, you're right. No. Yeah, Control L doesn't work. Then it's not climate science. the PPT. That's not me. Pourquoi gonfler les chiffres? I think we are going to. I can take mine if you like.
Sorry.
I can take mine if otherwise. Wonderful. Thanks so much. We're safe. Thank you. So I will also put again this graph, which is the projection for the next century of the temperature and the two scenarios, the two extreme scenarios. Actually, climate scientists have worked a lot on this one because essentially the effects are bigger, so you can see clearer signals. But there's only a few studies working on this scenario. Not a few, but much less studies, because it is, of course, more difficult, and even with a global model, to see the effects of changes and to see and to understand really what is going to happen. So I think we are, after the Paris Agreement, we are we have to focus more on these ones and understand what is going on with this type of situations. Sorry?
32 and 39 are the number of scenarios.
Yes, for the global models. Not the number of scenarios, but the number of studies. Yes, has been much less. Yeah, and especially at regional scales, there are only a couple of them, even the scenarios. Okay, just before the Paris COP, and it has been shown also here, we in the previous presentation, we have this scenarios which are leading to 2 degrees, which are in green, and the INDCs and the hypothetical continuation of INDCs towards the 2 degrees. But the target was 2 degrees, and the INDC range would lead to about 3 degrees, as Jean-Pascal showed. So just before Paris, we had this 2 and 3 degrees. What is the difference between 2 and 3 degrees? We had many calls from journalists saying, what is the difference between 2 and 3 degrees? And after Paris, the target was actually 1.5. So it was completely unexpected, although the 1.5 was already in Copenhagen. But it was said not so loudly by a few countries, essentially small islands, but very vulnerable. And now in the Paris COP21, there has been 100 countries calling for this 1.5 degree target. So 100 is not a few. I mean, it's a lot of countries. So We really need to care about this. And now we need to have a special report on the 1.5 degrees by 2018, I guess. Probably, most probably, we are going to have to write a report. The science is not ready for that, clearly. And then there are many challenges. So we started to meet with colleagues to see what does this 1.5 degree mean and what could we do. And actually there are many challenges. And this is really nicely recapped in this paper, Houches and Knuti in Nature Geoscience. You can read it, and it's very short and very clear. Actually, there is a number of issues to understand exactly how 1.5 degrees is different from today and is different from 3 degrees. That's the range of estimations that we have for the future. And also at the relevant scale, not just global maps with 1 point every 200 kilometers, because impacts are local and need more accuracy. What damages can be avoided by an additional half degree from 2 to 1.5? How does the regional climate react to mitigation and adaptation from land use and land management changes? This is a big issue, because if we are going to use a lot of mitigations, even in the far future, second half of the century, then the land is going to change a lot. We are going to use a lot of bioenergy. We are going to use, a lot of new technologies taking space, like PV, wind farms, etc., and other technology, and it will change the land use and the interactions between the land and the atmosphere. And this is clearly an emerging topic. Tipping points. To answer also one of the questions that was asked before, why 2 degrees? Of course, there is no threshold, but we know that there might be some tipping points in between, say 1.5 and 3 to 4 degrees. We don't know where exactly, especially for Greenland. We don't know if it's 2, if it's 2.5, and there's a need to do more, to know more about that. Finally, we're all aware that 1.5 is probably impossible in the short term, in this century maybe, or in the coming decades. But so there will be probably an overshoot of temperature, and then we have to go down to 1.5. So there is a lot of questions about how the Earth system reacts to a decrease of temperature and a decrease of CO2, especially the carbon cycle. I mean, if we are increasing the concentration of CO2, then the trees are growing, the forests are growing. But then, if we decrease the CO2 in the atmosphere, how will the forests react? So we know that there could be a rebound effect, and there is a need to better estimate these kind of things. So even the models and the economical models, I've been told, so I'm not a specialist at all, so on economy, but I've been told that economical models have been a lot trained in growing CO2 scenarios and not in decreasing CO2 scenarios. It's a bit challenging. And of course, there is also other issues like governance of geoengineering, of negative emissions, ethical issues. I'm going to touch just a few seconds about this topic. So I want first to report a few results that we had actually in a European project which was called Impact to Sea, which was precisely funded by EU, by FP7 after, I'm going to skip this, after the Copenhagen meeting, Copenhagen COP, and which was designed to investigate what could be the impacts of a world with a 2-degree global warming in more details than just saying the precipitation is going to be 20% more and the temperature is going to be 2 degrees more. Just a little bit with more detailed, and the project was funded for studying these impacts over Europe and a few key vulnerable regions, Bangladesh, Africa and the Maldives, especially the Maldives for the sea level. So the idea was to take the most recent regional climate simulations. So in most of what was presented in Jean-Pascal's talk, the scientists have used these global models. So these global models are used to predict the climate and the energetic of the Earth. But of course, they, in this case, had points every 200 kilometers or so. And there is a need to see the impacts and to see better the extreme events, such as the heat waves or heavy rains, to have a focus. And we, in general, use this, what we call limited area regional climate models, which do have a higher resolution and try to better resolve topographic effects and local flows. So at the moment, we could, over the past years, simulate the European climate over the next century, for the next century, with a spatial scale of 12 kilometers. That was technologically the most we could do. And so 1 point every 12 kilometers covering Europe. So this is not enough, because at 12 kilometers, the Alps are still very flat. They are not going up to, we don't see the Mont Blanc, of course. Mont Blanc should be at 2,000 meters or something like that. So it's very smooth. But still, it's much better than 1 point every 200 kilometers. We see the Mistral flow, we see this kind of flows and this kind of climates, some of the microclimates. We do not see the sea breezes, the valley breezes, so we do not see the local climate, but we really see the regional climate. So the methodology used in this project was actually that there were too few, as we said, there were too few low-end scenarios, RCP 2.6. This is the global models, but the regional climate models, there were only 3 simulations. So we could not make an assessment with only 3 simulations for the RCP 2.6. So basically, the idea was to look at the RCP 4.5 and take the result of the climate a bit earlier in the century. So it was not stabilized simulations. So the technique was to look in each model, each global model, which will be downscaled by a regional climate model, to capture the 2 degree and look at the time period corresponding to this 2 degree. Yes?
What is the 0.46?
0.46 actually is the baseline. The reference period was taken at 70 to 2000, 1970 to 2000. And from observations, we could say that it's 0.46 higher than the pre-industrial. So here, yeah, it's a bit tricky, because all the maps I'm going to show are relative to this current situation. So it's not absolute. No, in 2 dimensions, and usually there are 50 levels in the atmosphere. That's about it, 50. Because 1 point every 12 kilometers makes a very smooth view. No, because it's average. It's like if you average the topography over 12 kilometers. So, yeah, just to mention, here's the temperature for a 2 degree global warming for different areas of Europe. So the 2 degree, so it's relative to this 70 to 2000. So the 2 degree is actually here at 1.5 relative to recent period. And Europe is warmer actually than 2 degrees. Almost everywhere the British Isles are below, essentially because the North Atlantic, British Isles are under the influence of the North Atlantic sea surface temperatures, and it's the area, it's probably one of the area, maybe the area, where the warming is the lowest in the world, and the North Atlantic, northeast. So British Isles are below 2 degrees, but all the other countries are above. So I'm gonna skip this and show you maps because it's more clear. So if we look at the warming relative to 70 to 2000 of a 2 degree global warming relative to pre-industrial, then this is what we obtain in terms of summer and winter temperatures. So clearly there's a higher warming in the south of Europe and a higher warming here in the north of Europe for winter. So why is that? Because we have amplifying mechanisms. Essentially, the drought that is Jean-Pascal talked about in the Mediterranean. So it makes, of course, less precipitation, make of course, drier soils. And drier soils increase the temperature because the radiation is transformed in sensible heat instead of evapotranspiration. So it increases the temperature due to a feedback, positive feedback mechanism, but which has limits. We can talk about that. And we have the same kind of amplifying mechanisms in the winter over the snow. Essentially, if you have less snow, the albedo of the Earth gets less, and then more energy is stored in the Earth. So essentially, the message here is that actually the warming can be much higher and actually doubles in some areas relative to this 2 degree if we look carefully. So Europe is a vulnerable region. In terms of precipitation, we have seen also that more precipitation in the north, winter and summer, and less precipitation in the south. This has been said, and this is the robust areas, so we could use, in this case, 15 models and look at where the signal is robust, that is to say that 80% of the models agree. In terms of extreme events, so this is a picture I like to show because we had in Europe a very strong event in 2003, and so this is the observation here along after 1950 and before 2012, and we have this peak in 2003. And this is projected with all our simulations here in the 2 degree and 3 degree climate. So this is also to answer a little bit what would be the difference between a 2 and a 3 degree climate. Here we see that in a 2 degree climate, we do have some events, like about 20% of the time. But here in a 3 degree climate, it's almost every other year. It's basically 40% of the summer that we have an event. So by the way, it's the temperature around Paris. I forgot to say. Then this project looked at the impacts, and this is probably the most innovative part in different sectors, water, energy, agriculture, health, etc. And try to make an assessment for Europe. So I'm not going to show all the results, of course, but the most important, there is a large impact even of a 2 degree warming on crop yields. So this is a very important thing. It's not always a negative impact. For instance, yields of summer crops would increase by more than 20% in many regions of Central, Western, Northern Europe. yields of winter crops would decrease by 20%. So 20% is not, it's not a small number. It's a large number, 2 degrees. And then also all crops would provide lower yields in Southern Europe. So this is also a quite clear result. Here is just a result for maize, but we have maps for many, many crops. And actually you see that, so this is the distribution. You see that if we look at the mean, so there is a decrease in the production of crops in the south and an increase. This decrease is green, sorry.
Red.
It's minus, yeah. And you don't see the numbers, but here it goes up to 200%. So there's opportunities there also. Yeah. Yeah, so that's increase and that's decrease. Sorry. Not my slides. Electricity demand, also beneficial in general. Heating effect dominates in most countries. So here I plotted the value at risk, which is the 95, I'm not an expert either, but it's the 95% of daily electricity demand in gigawatt hour per day. So, so it's the increase or the decrease of this value per country. So this is clear that the heating effect of the warming decreases the electricity demand in many countries, especially in France, which is a lot depending on electricity, and except in Italy, where the heating, where the cooling demand is actually overpassing the heating demand in the future. So this does not, of course, depend only on temperature, but also on the way people heat their homes or cool their homes. Electricity production, so for technologies, hydro, wind power, solar power, thermoelectric. So this has some assumptions behind, especially for renewables. But for hydro, what we see, so every bar is a country. We have actually 2 bars per country. 1 bar is for 3 degrees, 1 bar is for 2 degrees. You have all the scenarios, so it's a bit complicated. But the main message is that the hydro power potential actually should increase in the future, except in southern areas like Greece, like Portugal, Spain, etc. Always the same. Wind power decrease in general, but a small amount. It's, we are talking about like something like 5 to 10%. Solar power, about the same, a decrease. So here we have, we can debate about that because there is a lot of uncertainty on that. The global models predict all an increase of solar, of radiation in Europe, and the regional models predict a decrease, all. So we are investigating this. So thermoelectric, so this is not really a lack of production, but this is essentially due to the regulation on river temperatures and river low flows. You cannot produce if the temperature of the water is too high because it kills ecosystems, essentially. And then if we project the amount of electricity that is produced or not produced due to this regulation and to warming, then we get down to 20%. But the overall picture is that it's actually not so good, actually, in Europe. But the same situation should happen in the US. We also have results. I'm not going to describe everything, but since we are here, it's not, I mean, it's a big economy. It's not a small one. Winter tourism, we're not going to have snow anymore. Not fully, no snow, but a reduction of the ski length season by by like 30 days, so a month. It's the order of magnitude. So reduction of the ski season of a month. And this results in a risk of a few million nights per season of a few million nights in the ski resorts. So this is not, this has some impact. So the main message is that the 2 degree is actually a lot of impacts compared to previous situation already, I think. And actually what some colleagues have done is try to look at a kind of winner and loser map of the impact of the 2 degrees by looking at hotspot in the positive and in the negative directions of the impacts and in the distribution of possibilities. So, for instance, they took hydro power and looked at where the hydropower was was increasing most and decreasing most at the other end. So increasing would be a winning situation, decreasing would be a losing situation, and then put the winners and loser maps by additioning all these hotspot counts, hits or counts. And yes, there's a pretty clear picture that there's going to be a lot of losing situation in the south of Europe for all sectors, for many sectors, because of drought, heat waves, etc., and a winning situation for Scandinavia because of reduction of electricity demand, of increase of hydropower, etc., etc. So this is the picture. It has to be taken with caution because we are with this in this analysis. It has taken into account only a few sectors, and it's becoming larger at the moment. All these results, I invite you to look at. It's a big European project, 29 partners, and all these results are shown in this atlas of impacts. Thank you. So the method has limitations. These are taken as transient scenarios. So we look at 2 degrees when it occurs in the coming decades. So that is basically in the RCP 4.5 at near 2040, in about 30 years. Non-stabilized scenario. So it doesn't take into account the sea level in particular, which is a much longer effect, as you said. Also, we are not, as climatologists and as climate modelers, up to the point currently to model everything. So we model the climate change due to atmospheric composition. We do not model yet at regional scale the climate change due to land use change. So this is something we have to worry. There's a big gap in the expectation. For instance, at 1.5 degrees, we have to do a lot of mitigation, a lot of bioenergy, etc. This will change the land, and we do not have that in our models at the moment. Also, 12 kilometers is not enough. We need to have more, especially for extreme events, heavy rain, and local adaptation. So at the moment, to go to the local scale, for adaptation plan, usually we use statistical techniques. I'm going to take an example on the resolution. So it might not be completely clear. This is an IPCC report on climate extremes, the SREX. And this map shows the increase in different scenarios and in different regions of the most extreme precipitations. So I don't know exactly, I don't remember exactly the indicator, but this is the increase in the most extreme precipitation. For Europe, for instance, in the mid-century, here it's about 10%. In the end of the century, a bit more. And we have about the same things in different areas of the world. But this extreme precipitation are not well modeled, actually. these models do not simulate explicitly the clouds, the big clouds, the cumulus clouds. And there is a need to go further beyond this. And the next generation of models should do that. I'm going to show a result of one study that we did last year on because we were stimulated by these big events we had in 2014 in the fall. As you know, maybe in the Cévennes area, it's in the south of France, there is a mountain range where it rains a lot, especially in the end of the summer, in the fall, September or October, because the Mediterranean is very warm, and when we have southerly flows, we start to have cold air in the upper layer of the atmosphere, and it creates a lot of convection, thunderstorms. And then in this range, we can have up to 500 or more in a day millimeters of rain, which is, 500 millimeters is what you get in Paris in 1 year. Then you get this in 1 day, and it can go up to, we have some measurements also, up to a meter in a day. So it's a lot. So we have investigated this, and as you see, these are different stations, all different stations, 14 different stations. They are very decorrelated. The rain do not occur at the same place. So these are very small scale features, thunderstorms. Here you have it at one station, and the other ones are not so heavy precipitation. But if we average this and look at different stations, what we see is not a few percent of increase since 1950, it's 30%. So we still have challenges in understanding these big numbers. Is this only natural variability? Is this climate change? Is this whatever, a change in the flows? And this is completely open, and our models are not able today to look at that. So this is the challenge for the next 3 years. Just to show you this is the observation. France, this is the seven mountain range here in the fall, the maximum fall values for the dailies. And it's really here that it happens, even in Europe, I think. And the models are, can hardly simulate half of the signal. So this is a poor representation, even at 12 kilometers. Now, my final, almost final point is that, and it's a difficult topic for me because I'm not specialist. Mitigation and negative emissions use resource and have a number of poorly assessed climate consequences. I'm going to show you a few of them. So this is a recent paper by Smith et al. In 2016, and it shows how this negative emissions technology, what they need. So negative emission technologies are usually bioenergy and carbon capture storage, what we call the BECCS. So we basically burn vegetation and put it in the ground. Or there's the CDRs, which are either the direct atmospheric capture of CO2 or the enhanced weathering of the minerals. We have forest bags. There are other technologies. And here are the constraints summarized here for a given target, which is 1 ton of carbon equivalent. This is the this is the constraint on land in hectares for 1 ton. So half an hectare here. I think it's in a hectare. Yes. Yes. And this is there are constraints on nutriments, nitrogen cycle. There are constraints on water. The afforestation and reforestation do take a lot of water and change the water cycle significantly. There are some recent papers on that. There are constraints on energy. I'm not going to talk about that because I'm not specialist. Costs either, you are the specialist. And probably albedo is very interesting also because if we change the land, we may have situations like in the boreal forest. In the winter, in the boreal areas, they are usually small trees or bushes. And when the snow comes over, then it's completely white. There's a strong albedo effect. But if you change this to trees, higher trees, then the albedo is higher. And in this study, they also claim that albedo is lower. Sorry, thank you. And it is also thought that this albedo effect could cancel the benefit, actually. So it would warm higher than what it would benefit. Just a few things I want to mention before concluding. Wind farms also induce change in climate, regional climate. This is a satellite analysis of the difference between the years where there was wind farms in Texas. So this is an area of about 80 kilometers to 100, and minus the time where there was no wind farm, 23, 25. So there's a clear, in the night especially, there's a clear warming in the wind farm areas. And so these are not so big. It's 0.7, it's local, but it's important to study. We have done a study as well on wind farms deployed in Europe with scenarios up to 2050 with a quite intensive scenario. So these are the wind farm production here in the maps. And these are the temperature effects. So it has to be taken with caution because it's only one model. And essentially, you could see a pattern in the winter where the full deployment of this wind farm scenario would lead to an increase of temperature up to 0.3 to 0.4 degrees in some areas and a decrease in other areas. Why? There are two effects. There are local effects of the wind mills breaking the inversion at night and in stable situation. So windmills actually take warm air, bring it down to the ground. And also here there is a larger scale effect, which a larger scale effect is that it actually deflects a little bit the winds, on average, a little bit the winds, and creates an anticyclone here on Europe. And then it's warmer here and colder here because the winds are more coming from the south here and from the north here. So it's a small effect, but still it has to be considered in assessment. My conclusions? Thank you. The Paris Agreement actually triggers a number of new climate scientific challenges. Regional and local consequences of altered and strongly mitigated climate must be assessed with a lot of models, not just one model. So we need many models because there are uncertainties. And definitely, and this report will be, well, I think this report will be voted, but I hope it will be voted actually, because even though the science may not be ready, I think we can make a clear statement of the gaps. I stop here. Thank you.
Thanks.